Hey everyone, welcome. You know that feeling on a roller coaster, right? That incredible rush when you plummet down a massive hill? It feels almost like magic, but what's really going on is pure, unadulterated physics. Today, we're going to pull back the curtain and look at the unseen rules that make that ride work, the hidden dance between energy and momentum. So let's start with the big mystery. You've got that slow click, clack, click climb to the top. It builds the suspense, but it's also building something else entirely. And then, whoosh, you're rocketing down the track. So where does all that amazing speed come from? And just as important, where does it all go when you start climbing the next hill? That's the puzzle we're going to solve.
All right, to really get this, we need to think about physics a little differently. It's not just about pushes and pulls. Think of it more like a transaction. We need to understand the actual currency of motion, which is something we call energy. And just like any currency, you got to earn it first. In physics, you earn it by doing work. Now, in physics, the word work has a super specific meaning. It's not just about trying hard. You're only doing work on something if the force you're applying actually makes it move. So think about it like this. If you lift your backpack off the floor and onto your shoulder, you did work. But if you just stand there holding it, no matter how heavy it feels, if that backpack isn't moving, you are doing zero work. Physics says so. Okay, so when you do work on an object, you're basically giving it energy. And that energy comes in two main flavors that we care about today. First, you have potential energy. This is like money in your savings account. It's stored up, ready to go based on where the object is. Then you have kinetic energy. This is the energy being spent right now. It's the energy of pure motion. So let's tie this back to our roller coaster. That long, slow climb to the very top, that's the park doing work on the cart. It's lifting it up, packing it full of gravitational potential energy. The higher you go, the more energy gets stored up, just waiting to be unleashed. It's literally a bank account of motion, and that climb is one big deposit.
And the second that coaster tips over the edge, that's when you make a massive withdrawal. All that stored potential energy starts converting into kinetic energy, the energy of speed. Now, look at that formula on the slide. See how the velocity, v, is squared? That is a huge deal. It means if you double your speed, you don't just double your energy, you quadruple it. It's why a tiny bump at 20 miles per hour is no big deal, but a crash at 80 is absolutely devastating. A little more speed equals a lot more energy.
So we've got this bank of potential energy at the top of the hill, and it gets spent as kinetic energy at the bottom. But how are these two things actually connected? Well, it turns out they are governed by one of the most fundamental, most elegant, and totally unbreakable laws in the entire universe. Let's just trace the coaster's journey. At the very top, it's barely moving, right? So its kinetic energy is basically zero, but it's as high as it's ever going to be, so its potential energy is maxed out. Then, as it plummets down, it's losing height and potential energy, but it's gaining speed, cashing in all that potential for kinetic. At the very bottom, it's at its absolute fastest, maximum kinetic energy, but almost no potential energy left. And this perfectly explains our big puzzle. It's the law of conservation of energy. The energy was never created out of thin air, and it never just vanished. The total amount of energy in that roller coaster system stays constant. It just swaps its clothes, changing back and forth between potential and kinetic, from stored energy to moving energy, and all the way back again. Okay, so energy explains the roller coaster's speed. I think we've got that down. But what about when things actually interact? When they crash into each other? For that, energy isn't quite the whole story. We need a new tool, a concept that describes the sheer quantity of motion an object has. We need to talk about momentum. Momentum is, well, it's basically a measure of unstoppability. It's mass times its velocity. And you know this instinctively. Imagine a huge truck and a tiny bicycle are both rolling towards you at the same speed. Which one is going to be harder to stop? It's not even a question, right? The truck has way, way more momentum. So how do you change something's momentum? Well, you have to apply something called an impulse. And the whole trick with impulse is that it's not just about how hard you push, it's also about how long you push for. So a small force applied over a long period of time can give you the exact same change in momentum as a massive force applied for just a split second. This is the secret behind airbags. The airbag doesn't reduce how much your momentum changes. You're still going from highway speed to zero, but it dramatically increases the time it takes for that change to happen.
And by stretching out the time, it massively reduces the force you feel. It's genius, and it saves lives.
This whole idea of transferring momentum from one thing to another becomes super obvious when we look at collisions. It doesn't matter if it's two billiard balls on a table or two galaxies colliding in deep space. Momentum has its own conservation law that tells us exactly what's going to happen.
And here it is, our second unbreakable rule for the day, the law of conservation of momentum. In any collision where there are no outside forces messing things up, the total amount of momentum you have before the crash is exactly equal to the total amount of momentum you have after the crash. Momentum isn't lost, it just gets passed around between the objects.
Okay, this is where things get really interesting, because energy and momentum play by slightly different rules here. Look at that momentum column. It's conserved, conserved, conserved. It always is. But now look at the kinetic energy column. See that? It's only conserved in a perfect elastic collision, where things bounce off of each other cleanly, like pool balls. In almost every real-world crash, which we call inelastic, some of that kinetic energy gets converted into other things, like the sound of the crash or the heat from bending metal.
So let's just boil this all down. What's the big takeaway? Energy and momentum are just two different ways of looking at motion. Energy is the currency. It tells you an object's state, like how fast it's going or how high up it is. Momentum, on the other hand, tells the story of interactions. It's all about how motion gets transferred from one object to another. And they're both conserved, just not always at the same time.
And that brings us to one last, really important question. If energy is always conserved, what about that real roller coaster that eventually slows down because of friction? Or the lost kinetic energy in a car crash? If it's not destroyed, where does it go? Well, it's transformed into forms we can't easily see or use, like the heat from the wheels rubbing on the tracks or the loud sound of the crash. The total is still there. It's just been turned into something else. So from that stomach in your throat feeling on a roller coaster to the life-saving physics of an airbag, the laws of energy and momentum are the hidden rules running the whole show. If this explainer helped you see the physics in your own world a little more clearly, you know what to do. Be sure to hit that like button and subscribe for more explainers just like this one. Thanks for watching.